Good morning all. My name is Amrei van Zyl from the University of Stellenbosch in South Africa. With my co-author, Dr. Vian Jooste, we set out to establish the feasibility of alleviating water shortages in the city of Cape Town, South Africa, using decentralized wastewater treatment plants. This investigation formed part of my PhD dissertation. So let's jump in. The city of Cape Town is an urban area with a population of over 4.1 million that is experiencing ongoing water stress driven by climate change with extended periods of drought, urbanization, pollution, and economic growth. The majority of the city's water demand is for potable water, which is sourced from surface water resources. Surface water resources in the Western Cape water supply system have already reached its economic viability, meaning it's not feasible to build more dams. The affordability and reliability of water resources impact the future and current investments of economic activities within the city. This highlights the economic importance of suitable and affordable water resources. At present, approximately only 10% of water is treated for reuse in the city of Cape Town, with the reuse limited to non-potable application for industry or irrigation. Not only are the Sustainable Development Goals for 2030 encouraging the increase of treatment of wastewater, but within the reuse sphere, there lies several avenues of value generation. The value of reusing wastewater extends further than cost savings. It also reduces the demand for constrained resources. In industry, the potential for effective reuse of wastewater can be derived from both centralized and decentralized sources. Centralized wastewater treatment plants offer non-potable water sources for several industry purposes, and decentralized wastewater treatment plants are implemented successfully in mines, using the treated water for a range of non-potable purposes on site. However, the majority of water requirements are attributed to potable water needs. To address the uncertainty surrounding the feasibility of utilizing decentralized potable water treatment plants in water-stressed areas, a case study was selected. Mutual Park in Pinelands, Cape Town, has implemented not only extensive water-saving devices and practices, it has also piloted a black water filtration plant, producing potable quality water for direct on-site consumption in 2018. The case study investigation brought to light several system parameters that was used to model the decentralized wastewater treatment system in Vensim. These parameters include the annual consumption, borehole abstraction limits, storage tank capacity, and the plant capacities of the system. To visualize the flows of different quality water within the system, a conceptual model for the Mutual Park campus water system was constructed. The blue lines illustrate the flow of potable quality water, while the gray illustrates the treated effluent or grey water from the municipality. Yellow presents the on-site groundwater, and black, the wastewater or black water. The losses are also indicated with red. Although wastewater can flow from the collection sump into the city's sewer system, wastewater cannot flow into the system from the city, even if the capacity for treatment allows for additional processing. The system receives water from the municipal sources, both potable and non-potable. Water also enters the water ring from 2 on-site boreholes and treated wastewater from the decentralized black water filtration plant. From here, the detailed system dynamics model was constructed. 2 stocks are identified: the Old Mutual storage tank capacity and the Old Mutual treatment plant capacity. I'll highlight some key functions. The system throughput is calculated as the total treated wastewater entering the system divided by the Old Mutual treatment plant capacity. The treated effluent from the decentralized City of Cape Town system can be used to supplement wastewater entering the Old Mutual system. The system dynamics model also accounts for system losses, both the process and consumption losses. Storage tanks take in the water from independent groundwater treatment system, which is treated to potable quality as well. It also takes potable quality water from the black water filtration plant. Water consumed sifted to reduce the amount of water stored within the tank. Other functions include Old Mutual consumption, based on the percentage of water saving, the amount of wastewater produced on-site. This function allows for future adjustment in the event that the City of Cape Town allows for wastewater from the centralized sewer system to flow into Old Mutual's wastewater system. This formula makes provision for the limit on treated wastewater entering the system based on the system's capacity. I've provided the calculations used in the model as additional information for those interested in further details. To ensure a level of confidence, the model was calibrated and validated using actual results obtained from Old Mutual technical reports. Variable model parameters are adjusted for 3 simulation runs based on 3 observations. Several parameters are fixed, including the annual water consumption, with a 30% reduction in usage from initial annual consumption. The system was designed to have a throughput of 75%, with an input from the central municipal treated effluent system of 25%. Throughput was not provided as part of observation A and B. However, the throughput was found to be significantly lower without the input from on-site boreholes. To establish the feasibility, scenarios for normal rainfall, dry periods, and droughts were tested using the Old Mutual decentralized potable quality wastewater treatment model. Commercial water and sanitation tariffs vary significantly with changes in water restriction levels, which are dependent on the availability of water resources for the City of Cape Town. Although water and sanitation cost savings can be made by substituting internal water demand with on-site treated effluent, the operating and capital costs need to be accounted for. The approximate reuse of wastewater on-site amounts to 53% of the total water consumed. With the supplementing centralized treated effluent set at 25%, there is still a requirement for municipal potable water. When calculating the total cost of the system for 3 scenarios, the total capital payback periods are found to be 8, 6.5, and 4 years respectively, when the system cost is 20 million rand. This period can increase significantly if the capital expenditure is more. Here are some calculations done to find the total cost implication of these decentralized wastewater treatment plants. When considering climate change, it is evident that there will be periods of drought, followed by periods of considerable rain, and as such the payback period may vary from the results presented. It is clear that the system dynamics model and associated simulated scenarios provide decision makers and investors with insight and information regarding the cost and operation of such a system. The impact of water supply stress is another feasibility factor that needs to be considered prior to the investing in decentralized wastewater treatment systems. Industries utilize approximately 30% of all water consumed in the City of Cape Town. Subsequently, alleviating water demand in the industry section can significantly reduce overall water supply stress. The consumption and allocation of water resources also vary with conservation measures or restrictions, constraining the allocation significantly. The number of decentralized wastewater treatment plants and their impact on water supply stress for both constrained water usage during periods of drought and unconstrained usage during normal rainfalls are compared. Using the water consumption and savings presented by the simulated results, the amount of water consumed by industries implementing decentralized wastewater treatment plants, similar to the one used by Old Mutual, are calculated. These values are used to estimate the potential saving that can be achieved. Water consumed and saved per facility is based on the consumption and water savings of the simulated Old Mutual plant. These savings are translated to the change in the City of Cape Town's water supply stress. Where a water supply stress of 1 or larger indicates that the water demand exceeds the available resources. It is evident that during normal periods, when the rainfall is sufficient, there is no water supply stress in the region. However, during drought periods, larger amounts of industries implementing these decentralized systems manage to bring water supply stress below 1. To conclude, I would like to emphasize the importance of sustainable future endeavors, especially in the reuse of wastewater as a valuable source of potable water. The City of Cape Town is actively encouraging the diversification of water sources to supplement constrained natural resources. It is evident that the reuse of wastewater for potable purposes has significant potential. However, these systems are not always economically feasible, as presented by the simulated results. Tax incentives have the potential to provide investors with added encouragement to consider the implementation of decentralized wastewater systems, as these systems also offer industries the needed assurance of available quality water. These factors need to be considered during decision-making. It should also be noted that the study found that the decentralized systems are inherently connected to the larger centralized system. Finally, the system dynamics model constructed using the old mutual case study can be adjusted to serve as a supporting tool for decision makers and investors for other specific systems or parameters. The scenario development and results provided insight into the feasibility of private investment into potable wastewater treatment plants, highlighting the variances in payback periods and the efficiency of these systems during drought and normal rainfall periods. I would like to thank you for listening to my presentation. Are there any questions?